as we continue our journey in the anatomy of mathematics, of figuring out different features of graphs that we can analyze, that we can look for, and then we can find ways to determine whether they are true for a graph or not, the next one, as we continue in this section of notes today, is going to be graphical symmetry. So what types of symmetry graphs can have. So these first three graphs all have some type of symmetry. I want you to take a second and I want you to look at them and see what types of symmetry you see in these graphs. If you want to pause the video for a second, if you need time to think about it, pause, and then I will talk about what symmetries are going on here. So if you look at the graph in letter A, when we talk about symmetry, we think about if we could draw, often we have symmetry over a fold. So if we could draw a line down a point, the graph or the image is exactly mirrored on either side. So in our first case, we have symmetry mirrored from left to right, and the line that is determining our symmetry is the y-axis. So it looks like the axis here is what this graph is completely mirrored from left and right. If I folded it in half, they would be symmetrical. So this is what we would call symmetry about the y-axis. Similarly, when we talk about folding, let's jump over to C. Maybe this one was also a little bit easier to notice. When I look at graph C, this also could be folded across a line. Instead of being the y-axis this time, I could fold this graph completely across the x-axis. So being symmetrical with our axes, so this is x-axis symmetry, being symmetrical with the axes is a very common and a pretty important type of symmetry that we're going to find. So this last one, if I tried to fold in half, the curve on the right is definitely not going to sit. It would look something like that. So that is not symmetrical by folding it, but I could rotate it about the point 0, 0, the origin, and the different points, if I rotated it a full half circle, 180 degrees, so the point that's up here could come all the way around a half circle and end up over here, and so on and so forth for the rest of our points. So this is what we call 180 degree symmetry around the origin. So here are three graphic examples of the three types of symmetry that we're going to see today. So just like I have mentioned with domain range, x-intercepts, y-intercepts, what we want to do in this class is be able to look at a graph and determine graphically what these features are, if in this case, if symmetry exists. But we also want to find when graphically I see symmetry, what is happening with the equation that corresponds to that graph, and how could I test for symmetry if I'm just looking at the equation? So that's what this whole chart's about. So I've already got some of this written out in here. If you need to take time to pause and write this in, please do. That's the great thing about a video. So I'm going to talk through what you want to look for with a graph. So for the x-axis symmetry, we want to be symmetrical about the x-axis. So if you folded it along the horizontal, along the x-axis, the graph would land completely on top of each other. So I've drawn a model here of a sideways absolute value function that shows x-axis symmetry. So you can first graphically look at it to determine symmetry, but the way to be absolutely certain is that whenever we have x-axis symmetry, what's going to happen is that if our graph, if we pick a point x, y, that the graph passes through. So let's say, for example, that this graph passes through the point, let's say this point is 3, 2. So I pick a point that the graph passes through. So if the graph passes through 3, 2, it's also going to pass through what we call x, negative y. So that means it will also pass through 3, negative 2. And if I think about that, that should be, 3, negative 2 should be right somewhere around here. And that would make sense. If I go straight down, the x value should stay the same, but the y value should flip. So that is our way to test graphically. And when we look at a graph, I'm going to encourage you to pick a couple of points and then apply this rule to it. Make the y negative and see if the graph is also going through that point. That is a great way to make sure that your graph actually is symmetrical to give us some certainty here. Next up, for the algebraic test, if I have the equation, how do I work with the numbers to see if it's symmetrical? So what's going to happen is if I have my function f of x, if it is symmetrical across the x-axis, it will be equal to the negative f of x. So I take my entire function and I make the whole function negative, meaning I switch every sign in the equation. And when I do that, it will come out and it will be equivalent to the original equation. And you'll see how this works when we get to some examples later. So if it seems abstract now, we will do examples in just a second. So that's the x-axis. For the y-axis, so here in the middle, we have our model. This is an upside down parabola in this case, but there are many different types of symmetry through the y-axis. You could fold it along that vertical. So similarly, there is going to be a point test here. If I select a point x, y that my graph passes through, in this case, rather than x negative y, it's the x value that stays negative, that goes negative, and also the graph will pass through it. So the graph will also pass through negative x, y. So let's see here. Since I don't have specific equations for this example, I am just picking points that look like the graph is passing through. So let's say that this point right here looks something like 1, 3. Well, if I were to think about taking the point that is symmetrical just on the other side, if I think about that, that becomes -1. So this point is -1, 3. So it would seem reasonable that if it passes through 1, 3, it is also going to go through -1, 3. For the algebraic test, rather than we are going to add a negative into the equation, but instead, for the algebraic test for the y-axis symmetry, we want f of x to be equal to, we want f of x to be equal to f of negative x. So remember when I asked you to evaluate something like f of 3x, or f of 1 minus 2a, we are going to put a negative in every parenthesis with the x and then simplify it out. If it's symmetrical across the y-axis, the end result equation will be the same as the original equation that we were given. All right, so our last test here is going to be our 180-degree rotational symmetry about the origin. You'll often see it kind of called by two names. You'll see origin or 180 degrees. So for our last test, to look at points to determine graphically if it is in fact symmetrical with respect to the origin, again, we're going to select a point that our graph passes through x, y. If the graph passes through xy, it's also going to pass through -x, -y. We make both negative. So let's say here, this is the point 1, 1. If I think over here, this point, the x becomes negative, the y becomes negative, so it would make sense that it's going to be -1, -1. And so if we think it is rotational, we can pick some points and verify that they do cross through our graph. Okay, so then lastly, for our test, what we want to determine is that our original function, f of x, in this case, we are going to do two things. We are both going to make the entire function negative, and then we are also going to put a negative inside. So we want the entire function to be negative, and then we're going to put a negative x inside, evaluate it, and if we do both these things, it's telling us that we should get back to our original equation once again if it is symmetrical. So these are the rules. Couple of tips before we move forward is I always think about the negative sign that switches for the x and y axis is opposite of what symmetry we're dealing with. So if we're dealing with being symmetrical across the x axis, it's going to be the y value that the negative version is also on our graph. If it's y-axis symmetry, it will be the x-axis. So it gives us that kind of flipped mirror, just kind of like with the x-intercepts, that's where y is 0. Often where we're talking about an x category, there's something dependable happening with the y because it keeps y steady for us. So let's see some examples. What does this actually look like in practice? So here is a graph here. First, I want you to think, as I look at this graph, what do you think the symmetry is? I'm going to give you a second. So I would say that this definitely can be symmetrical by folding it. What axis is it? It is the y-axis. So visually, I would say that this looks like this has y-axis symmetry. But here's what we're going to do. We are going to make a little t-chart to pick maybe 2 or 3 points to confirm the point rule that we said, which is that if we had a point x comma y, it's the y-axis, so that would be negative x, y is also going to be on our graph. So I'm going to go to quadrant 1 and pick a couple of points here. So let's see here, let's pick this point. Over here, it looks like that is 1, 3. And then maybe up here, this is 2, 4, 5, 6. So this is 1, comma 3, and then this is 1, 2, 3, 4, 5, 6. This is 2, comma 6. So we're saying that the point 1, 3 is on our graph and the point 2, 6 is on the graph. So now the question is the point negative 1, negative 3 on the graph. If I go to negative 1, or sorry, negative 1, positive 3, if I go to negative 1, 3, there we go. This is the point negative 1, 3. My graph does pass through it. If I go over 2, up 6, do I land on the graph? And indeed I do. So this means that negative 1, 3 and negative 2, 6 are also on our graph. So these 2 points give us a pretty good idea that this symmetry is working. So this is how we confirm graphically. You can first use the visual and then use this point rule. Next up, we need to confirm this answer algebraically. So let's say I did not have this graph. All I had is the equation y equals x squared plus 2. So going back up, the rule for y-axis, it's our middle, our middle box, is f of x needs to be equal to f of negative x. So what we are going to calculate is f of negative x. And we want that, we're trying to figure out if that equals x squared plus 2, which is our original equation. So for f of negative x, wherever I see an x, I'm going to put a negative in the parentheses with it. So that becomes negative x squared plus 2. Well, what happens when we square a negative? It becomes positive. So this becomes x squared plus 2. When I check back to my original equation, that is the same as f of x. So that equals our original f of x, which means check this graph is symmetrical about the y-axis. All right, awesome. So let's do another one. This one's symmetrical about the y-axis. We did our graphical test and we did our algebraic test. Number 2, first thing you want to do, use the visual. What do we see? What's going on here? Let's take this graph in. This is, I can't, I could fold it across a line, but I can't fold it across the line, either of the axes here. And so if I rotated this about the origin, I can see that the section in quadrant 2 would rotate all the way around to quadrant 4. So it looks like here that we have symmetry about the origin. So what we're going to do real quick is test some points. Our point test for going around the origin was that xy should also, if I have xy on the graph, I should also have negative x, negative y. So with this graph, it is counting by 2's on our line, so we should look here for some points. I'm going to select, let's see here. Looks like maybe right here along this line at 6. Since this is 2, that means this is 1. So I'm going to say that this point here is negative 6, positive 1. So let's switch this. If I switch the x and I switch the y, I should expect to find the point +6, -1 on the graph. So let's go over to where that is and let's see if our graph is passing through this. So +6 is over to the right, somewhere around here. Go down to -1 and look at that. We do end up back on this graph. For the sake of time, I'm just going to try this one, but you can pick a couple others and see if it works. So graphically, I would say that we have confirmed that we do have origin symmetry here. But now we need to confirm our answer algebraically. So here is what we are going to do. We are going to, now I'm going to actually go up and add one rule here. So what this f of x, the negative f of negative x, what this means is we're making y negative and in the equation and we're making x negative. So an alternate way to do this is to, if we have x and y, just like we did with our point, we are going to make sure it equals -x, -y. So replace x with a negative and also with y. So what that looks like here, because this equation is not solved for y, I have xy equals -6x. So what I'm going to do is I'm going to make the x negative. So that makes this, oops, give me just a second. That makes this -x. And we're also going to make y negative. So -x times -y equals -6. And once we multiply those out, two negatives multiply to make positive. So that becomes again positive xy equals -6. And this is same as our original equation. So this is how we confirm. We have made all of our x's negative and we have made all of our y's negative, which is just that one x and that one y. And this is how we can confirm this and do our test for origin symmetry. So we are in fact confirmed symmetrical around the origin. Okay, let's go ahead and talk about, once we've talked some about symmetry, and in the practice that we're going to do when we get into class on Monday, we are going to do a lot more work with symmetry. So if you see these tests, you feel like you need a little bit more work, we're going to do some more examples together. We're also going to do a lot more group practice on this, so we will get more practice come with questions on Monday. Next up, for our even and odd functions. This is another, again, we are adding to, as we're uncovering more about graphs, we're figuring out more features. So we have x-intercepts, we have y-intercepts, now we have symmetry, and then next up we have a type of function that can be described as even and odd. And if you were tracking with what we were talking about with symmetry, this next section should be very easy because even and odd is actually just another descriptor for specific symmetries. So first up, we have functions, the definition here, and then I'm going to tell you which one is which. Functions that are symmetrical with respect to the y-axis. So any function we've seen so far that is symmetrical to the y-axis is what we call an even function. So that function is even. So our algebraic test for an even function, just like we already did, is for every x in the domain, we want f of x to be equal to f of -x. And the reason we call it even, the further we get into functions, we're going to find that the highest exponent in your function is going to correspond, it is often going to be even, which is what allows it to be symmetrical to the y-axis. So there is a connection to the power, if it's even or odd, in whether it is symmetrical to the y-axis, or our second one here, now that we talk about odd functions, you would think that odd functions, since even are y-axis, it would be x-axis, but it is not. Odd functions are functions that are symmetric with respect to the origin. So this is our rotational symmetry. X-axis is left out of this one. It's not a special type of even or odd function. So if it is symmetrical to the x-axis and it asks even, odd, or neither, the answer would be neither. So for our test for the odd function, just like we've said before, we want to say that f of x needs to be equal to the negative f of negative x. So f of x needs to be equal to the negative f of negative x. Or for every x, we replace it with negative x, and for y, we replace it with negative y, and it should come back and equal our original equation. All right, so here we go. Graph the function f of x equals x squared minus 4x plus 4 on our graphing calculator. All right, so now I'm going to go ahead and open up our graphing calculator and put it here on the split screen. If you have forgotten how to graph this, hopefully will be a great using your calculator. And you can use Desmos for this, but I want us to start getting comfortable using the calculator. So we are going to click the y equals button. All of the graph buttons that we want are going to be in the top kind of black section right under the screen. They're going to be those 5 gray buttons. If we're graphing, that is our sweet spot unless we're typing stuff in. So now we want x squared minus 4x plus 4. Remember the x is right to the right of the alpha button, the green button. Then we want to check you always want to check your window. Otherwise you'll click it and you might not see the graph. So looking here, my window, it's saying things a little weird, but it is going x minimum. So the furthest left number is negative 10, furthest right is 10. That is good. That's what I want. I'm sorry, it's being a little weird with the view this morning. So this is a nice standard window. I look at that, I can see the x-axis and y-axis, awesome. I graph this, and this is definitely, it has some symmetry, but does it have x-axis or does it have y-axis symmetry for even, or is it rotationally symmetrical about the origin? No, neither of those things is happening here. So in this case, we would say it is neither even or odd. So it's none of the above. But let's say we didn't have a graphing calculator and we needed to test them. We're going to test both of our rules for algebraic to see how this works. So first up is, let's just go ahead and do even first. So if it's even, I need f of x to be equal to f of negative x. So let's go ahead and do this. So f of negative x, here's how this looks. So we are going to do negative inside, or wherever I find an x, I'm going to do in parentheses negative x squared minus 4 times in parentheses negative x. I'm putting a negative inside the function with this. Okay, then negative x squared becomes positive. Then negative 4x times negative x becomes a plus 4x, and then plus 4. Is it an exact match with our original equation? No, this does not equal f of x, which means it is not even. So now we have done the algebraic test that confirmed what we saw graphically. It is not even. So for an odd function, this is where I need to switch both the x and the y. So this is f of x equals negative f of negative x, or switch x and y. So this is how this works. How I often will do it is I will start and I'm going to replace y with f of x, and I'm going to call this negative y. And then just like we did with all the x's, I'm going to make them negative. Negative x squared minus 4 times negative x, and then plus 4. Now we're going to clean it up, and then eventually we need to get rid of the negative in front of the y. So I am running short on space here, so I'm going to move this right over here. Actually, that didn't work for us. Give me just a second. Let's move this down here for just a second. Okay, so here's what we're working with. So now let's keep cleaning up. We have negative y equals, this we know becomes positive x squared plus 4x minus 4. Lastly, I want it to equal positive y, so I'm going to multiply everything through by negative 1. So multiply by negative 1. And this becomes positive y is equal to, now distribute that negative, negative x squared minus 4x sorry, this should have been a plus 4, minus 4. And this is our odd function transformation. So does what we just created, is it an exact match with what I see highlighted in yellow, x squared minus 4x plus 4? Definitely not. We've got a bunch of signs that are not as they should be. So that is another way to check to confirm what we saw graphically, that this is not odd. Okay, this is your chance where I want you to give it a try. I will work through this again. So if you feel like you saw that, your head is spinning, you're not sure what's going on, you can go through this example with me, but I would encourage you to pause, believe in yourself, give it a try, and see if you can try some of these tests here right now on your own. So if you want to do it on your own, pause. You can always restart the video and I will keep going here. So we're going to do, I believe this is our last one. Yep, we're going to do one last one together before these notes finish. And then when you come back to class, whether that's this Monday or this Wednesday, we're going to do a lot of group practice together on this. So graph the function g of x is equal to x squared minus 5 on our calculator. Let's go back into y equals. You can use Desmos. I'm just trying to get us comfortable with the graphing calculator. And I already have an x squared, so I'm going to delete some of these. And we have x squared minus 5. Look at that. What do we think? I would say that this looks, it's symmetrical about the y-axis, which means that this is going to be an even function. So here we would say that this is even because we have symmetry about the y-axis. Symmetry about the y-axis. Okay, so now that we have looked at this graphically, feels pretty good, let's confirm it algebraically. We only need to do even, which means we want to replace x with the negative. So f of negative x should be equal to negative x squared minus 5. We've seen this a lot. We square a negative, it becomes a positive, so this gives us x squared minus 5. Look at that. That is the original. This matches exactly to our original equation, and I should have been writing g of x. That was bad. Let me switch this because we're working with the g function. Okay, so this means for us here that g of negative x was equal to g of x, which implies for us here this function is even. Okay, so this concludes our section on symmetry and on even and odd functions. As I've said, we're going to do a lot more of this when we come back together. The last thing that I want you to do to conclude that you have done these videos is this last example is yours to do on your own. I want you to graph it on the graphing calculator or Desmos, test for symmetry, and then once you do that, I want you to confirm that any symmetry you find algebraically, and then lastly, answer if it is even, odd, or neither. And then you will be done with your asynchronous assignment for this week. Thanks for listening in. Make sure that you write notes of your questions, that you come ready to ask questions, to review this, and to practice this when we start back a class in person on Zoom.